A Nimitz-class aircraft carrier displaces approximately 104,000 metric tons of water when fully loaded. Its flight deck stretches 333 meters in length. It carries up to 90 aircraft, millions of liters of aviation fuel, thousands of tons of ordnance, and a crew of over 6,000 people. It operates continuously in some of the most hostile marine environments on Earth, and it is designed to absorb catastrophic damage, flooding, fire, explosions, and continue operating. Most ships, when they flood, sink. The water entering the hull increases the vessel's weight faster than its buoyancy can compensate, and the ship goes down. An aircraft carrier is designed so that this sequence of events cannot complete itself under any realistic damage scenario short of total structural destruction. Understanding why requires stepping back from the carrier's size and starting with the physics of why any ship floats at all, and what it actually takes to make one sink. A ship floats because the weight of water it displaces equals its own weight. This is Archimedes' principle, and it applies to every floating object regardless of size or material. A steel ship floats not because steel is light, but because the ship's hull encloses a large volume of air, making the average density of the entire ship plus enclosed air system less than the density of water. As long as that enclosed air volume is preserved, the ship floats. When water enters the hull and replaces the enclosed air, the average density increases. When it exceeds the density of seawater, the ship sinks. The question of whether a ship sinks when flooded is therefore a question of volume. How much of the ship's internal volume can flood before the remaining enclosed air is insufficient to keep the ship afloat? And, critically, how is that internal volume organized to control which spaces flood and which do not when the hull is breached? This is where compartmentalization becomes the central engineering principle of warship survivability. The interior of a warship is divided into hundreds or thousands of watertight compartments, spaces bounded by watertight bulkheads, decks, and closures that prevent water from flowing freely between adjacent spaces when one compartment is breached. If a torpedo or a mine opens a hole in the hull, only the compartments directly connected to the breach flood. The watertight boundaries contain the flooding. The remaining compartments retain their air volume and their buoyancy contribution. The Gerald R. Ford class, the U.S. Navy's most modern aircraft carrier design, incorporates over 2,500 watertight compartments. The ship is divided vertically by watertight bulkheads and horizontally by watertight decks into a three-dimensional grid of isolated spaces. Each compartment can be sealed independently. Each watertight door, hatch, and penetration in a watertight boundary is designed and tested to resist the hydrostatic pressure it would experience if the adjacent compartment were fully flooded. The damage stability standard that governs U.S. Navy carrier design requires the ship to survive flooding of any 3 adjacent compartments anywhere in the hull and remain afloat with positive stability, meaning it rights itself rather than capsizing if heeled by wave action or flooding asymmetry. This is an extremely demanding standard. Most commercial vessels are designed to survive flooding of a single compartment. Warships are designed to survive multiple simultaneous flooding events because combat damage does not arrive in neat, isolated increments. Stability, the ship's tendency to return to an upright position when disturbed, is as important as buoyancy in determining whether a flooded ship survives. A ship can have sufficient buoyancy to remain afloat, but insufficient stability to remain upright. When a ship lists due to asymmetric flooding, the righting moment that returns it to upright depends on the relationship between its center of buoyancy and gravity. If flooding raises the center of gravity above a critical point, or shifts it so far that the righting moment cannot overcome the list, the ship capsizes. Capsizing is often more immediately fatal than sinking. A capsized ship loses all functionality instantly, while a slowly flooding ship may remain operational for hours. Aircraft carrier design manages stability through the same compartmentalization system that manages flooding. When flooding occurs on one side, the damage control system can counterflood, deliberately flooding compartments on the opposite side to restore trim. Counterflood tanks are pre-positioned throughout the hull specifically for this purpose. The process reduces the ship's overall reserve buoyancy, but it maintains stability and keeps the flight deck level. This is critical because a listed flight deck cannot safely operate aircraft, and a carrier that cannot operate aircraft has lost its primary function. The damage control organization aboard an aircraft carrier is a full-time operational capability, not an emergency response team. Over 300 personnel are assigned to damage control duties, organized into repair parties stationed throughout the ship at pre-assigned positions. Each repair party is responsible for a specific zone of the ship and is trained to respond to flooding, fire, and structural damage. They are equipped with portable pumps, patching materials, shore-up timber, and firefighting equipment staged at their repair lockers. Their training is continuous. Damage control drills occur regularly throughout every deployment. The skills required to contain flooding in a combat-damaged ship degrade rapidly without practice. The flooding response sequence is precisely defined. When a breach occurs, the immediate action is boundary setting, identifying the watertight boundaries surrounding the flooded space, verifying that every door, hatch, and penetration is sealed to prevent the spread of water. The pumping capacity aboard a carrier is substantial. Fixed installed pumps with capacities measured in thousands of liters per minute are distributed throughout the hull. Portable submersible pumps can be deployed by repair parties to any flooded space accessible through the watertight boundaries. Eductors, jet pumps that use high-pressure fire main water to create suction without moving parts, provide additional dewatering capacity that does not depend on electrical power. The combination of fixed and portable pumping systems allows the ship to manage flooding rates that would overwhelm any single pump. Fire is the companion threat to flooding in combat damage scenarios, and the two often occur simultaneously. A weapon that breaches the hull may also ignite fuel or ordnance. The carrier's firefighting systems are designed with the same redundancy as the flooding systems. The fire main, the ship-wide high-pressure water distribution system, is a looped network so that a breach can be isolated while the remainder continues to supply water. Aqueous, film-forming foam systems protect the flight deck and aviation fuel storage areas. Carbon dioxide fixed systems protect machinery spaces. Halon replacement systems protect electronic spaces. The aviation fuel system presents the most significant fire risk on the ship. A carrier may carry up to 3.5 million liters of JP5 jet fuel, a fuel specifically selected for its higher flash point. This reduces the risk of ignition from heat sources that would ignite lower flash point fuels. The fuel is stored in tanks below the waterline, surrounded by seawater ballast tanks that provide both thermal insulation and a physical barrier. Fuel transfer to the flight deck is through a closed, pressurized system that minimizes the exposure of fuel to open air. Despite these precautions, aviation fuel fires have caused catastrophic damage. The 1967 USS Forrestal fire killed 134 sailors and destroyed or damaged 21 aircraft. This remains the most significant peacetime carrier casualty and directly drove changes in damage control training and procedures that remain in effect today. The structural design of the carrier hull contributes to survivability in ways beyond compartmentalization. The flight deck of a Nimitz or Ford-class carrier is constructed from high-strength steel approximately 65 millimeters thick. This is thick enough to resist the blast and fragmentation effects of weapons that detonate on or near the surface. The armored deck distributes blast loads across a larger area, reducing the penetration depth of weapon effects into the ship's interior. Below the flight deck, the hangar deck provides a second structural layer. The combination of armored deck, structural depth, and the ship's mass means a weapon must penetrate considerable material before reaching critical systems. The underwater hull is protected by the ship's internal arrangement rather than by armor in the conventional sense. Critical machinery, propulsion systems, electrical generation, damage control systems, is arranged so that no single weapon hit can disable all redundant systems simultaneously. The carrier has 4 independent propulsion shafts, each driven by separate turbines in separate machinery spaces. A hit that floods one machinery space does not disable the others. Electrical power is generated by multiple independent systems distributed throughout the ship. The principle of separation, keeping redundant systems physically far apart, is the primary survivability design strategy for systems that cannot be armored. The limits of this system are worth understanding precisely. Compartmentalization and damage control manage flooding and fire within the ship's designed damage envelope. Beyond that envelope, when the number or severity of hits exceeds what the system was designed to survive, the outcome changes. No warship is unsinkable. The design standard specifies what the ship can survive, not that it can survive anything. The designed damage envelope for a carrier reflects a judgment about the threat environment and the acceptable level of risk. A carrier represents an investment of approximately $13 billion and the lives of 6,000 people. The design reflects the importance of preserving that investment and the recognition that a ship designed for every threat would be unbuildable. So, why doesn't a carrier sink when flooded? Because the internal volume is organized so flooding affects only a controlled fraction of that volume. Watertight boundaries preserve the buoyancy contribution of the remainder. The damage control organization responds immediately to contain flooding, restore stability through counterflood, and maintain the ship's ability to function. And because every critical system is duplicated, separated, and arranged so that no single damage event can simultaneously eliminate all redundancy. The carrier does not survive damage because it is too large to sink. It survives because it was designed specifically to survive damage, and because 300 trained personnel are stationed throughout it at all times, ready to execute that design's intent the moment it is needed. If you're thinking about what happens when damage control fails and the ship begins to lose stability, that's something I've covered in another video.